Hi everyone. I thought it would be good to do a fairly detailed tutorial on Slitherlink. I'm going to do this over 2 videos. This video will cover regular classic Slitherlink on a square grid, and the second video will cover what I call variety Slitherlink, where it's on non-square grids. Both kinds of puzzles are represented in my book Kaleidoscope Puzzles, which you can get, and it's got lots of these, and there are also tons of them on my website. So let's talk about what a Slitherlink is. This is what the puzzle looks like, and this is what the solution looks like. In the solution, there will be a path. The path will form a circuit or loop connecting to itself. So if you were to, stretch this out, it would form a giant circle or square. That path has an outside and an inside. And the clues tell you how the path goes around that particular cell. So this 2 clue says that 2 of the edges of this cell have path going through them. This 3 has 3 sides going through it, and I will commonly say the edges are filled, meaning they have lines, versus being empty or ruled out. The 0 cell here, there's no path going through that. The 1 cell here has 1 edge being used. I'm going to clear the puzzle, and let's talk about the tools. The pencil tool is used to draw lines. The X tool is used to indicate areas where the path can't go. I'm doing it wrong right now, but you get the idea. After you have filled out some path areas, you can use the colors to indicate inside and outside. My personal convention, which may differ from yours, is to use blue for the inside and yellow for the outside. But you can do it however you like. Some people like to use yellow and they think of blue as ocean, being outside. I think of blue as being good and yellow as being desert. But, everyone's different. Normally, I don't use these icons when I'm solving on the desktop. I use the keyboard because it's more efficient. So if you leave the pencil tool selected, you can draw lines. If you use the Shift key, you can make the X's or clear the X's. If you use the Command or Window key, it'll fill it in blue. And if you use the Alt or Option key on a Mac, it fills it in yellow or clears it. So you can pretty much do this whole thing with a keyboard. Just play around with the different Shift keys to get a feel for how they work. I'm going to go ahead and start over. Okay, so the way most people solve this puzzle is they have a collection of patterns that they've memorized. And we're going to go through some of those patterns as we solve this puzzle and the next one. But it's important to understand why the patterns work and what the principles are behind the patterns, especially if you transition from the classic Slitherlinks like this to the variety Slitherlinks. It's very important to understand the principles of the patterns, because the basic patterns that you use for classic Slitherlink won't work if translated literally. A beginner might solve this puzzle by just choosing a cell and going, okay, well, there's 2 around this 2 and 1 around this 1 and 3 around this 3, and just keep going that way and attempting to solve the puzzle that way. And you might get pretty far, but chances are your solution is wrong. In fact, if I check the answer here, I can already see I've made several mistakes. So that's not how to solve this puzzle. The way you solve this puzzle is by solving little pieces, a piece here, a piece here, a piece here, each time making deductions that you know to be true until eventually the entire thing is laid out. Don't attempt to just draw the entire path. You'll get into trouble very quickly. The first thing I usually look at is the corners. There's a 3 in this corner and a 3 in this corner. Corners create constraints. In a 3, only one cell can be empty. If this top cell were empty, we would have this situation, and the path would have nowhere to go in the corner. And the same is true if it was like this. So when a 3 is in the corner, the outer edges are always filled. Same with this 3 here. And when a 1 is in the corner, which does not occur in this puzzle, let me see if I can find one where it does. Here's a puzzle with a 1 in the corner. Then the outer edges are always empty, because if you were to travel along this path, you would force the 1 to have 2 edges. So corners are usually a great way to get started. Now, one of the first patterns most people learn is what to do with 3s that are adjacent, that share an edge. Like these 3 3s here, these 3, these ones here. And the general pattern is, I'll show you the general pattern and then we'll talk about why the pattern works. The general pattern is fill in the lines that separate the 2 3s, fill in the outer lines, and then put X's on the middle. For a longer 3 like this, you do all of them and then you put X's on the middle ones, like that. Why is this true? Why does this pattern work? You should understand that. So the important thing about this is that the 3 is the largest clue you're going to encounter in this puzzle. It's the number of cells minus 1. You're not going to see a cell with a 4 in it, because if you did, every single edge would be filled and it would be a very small, boring puzzle. Now, why is the center one filled? Well, what would happen if we didn't fill it? If the center cell had an X in it, the 3s would form this little shape like that, which again is a very trivial puzzle and does not occur in Slitherlink. So the center edge must be filled. Why is the outer edge filled? Well, if the outer edge was not filled, you would have this situation and you would be unable to complete the 3 on the other side. That is why the outer edge is always filled. Why is there X's on these inner squares? Let's do it over here. If there was not an X here and it exited like this, there would be an open edge here. This 3 would go like that, and we would be unable to complete this 3. That's why there are X's on the middle edges. So let's do all the 3s. Boop, boop, boop. Any more? Yeah, there's 3 up here. Boop, boop. And go ahead and do the 0. It's another thing I will do very quickly. Now I see I've got a 3 here. As soon as you have a 3 that has an X on it, you can go ahead and do the rest of it. And because of the 0, we can go to the side there. This 3 is finished. And what happens with these chains of 3s is that they always do a zigzag pattern like this. So once you've got one of them, you can go ahead and do the rest of them. This 2 has 2 edges we can't use, so we can go ahead and do the other one. You don't have to fill in X's everywhere, but it can be helpful to solve the puzzle. I see that there's an edge on this one, so I put an X here to remind me that the path doesn't go here. Having done that, I can see that the 3 can be completed, and the path goes up here. This 2 is completed, so the path goes up there. Another common pattern involves 3s that are diagonally adjacent, sometimes in a chain, and share a point. In this particular case, what happens is invariably the outer edges are filled when you have this configuration. Why is that? Well, let's imagine that this edge was empty. What would happen in that case is we'd have something like this, and we would be unable to complete this other 3. So for this reason, the outer edges must be used, and there's going to be a connection going through this dot, either that way or that way or that way. Okay. Sometimes after you've done a bit of the puzzle, you create what are essentially corners. This is essentially now, because of this edge has been ruled out because of that corner, is essentially a corner for this 3, and so we can go ahead and fill in the 2 edges there. Otherwise, we'd be unable to complete this 3. That completes this 2. In this chain of 3s, because of the 0, we've already eliminated an edge on one of the 3s, and that allows us to finish out the chain. This path is forced to go this way, which finishes the 2. Now we have another 3 with a missing edge. That forces the path over here. And now we keep forcing this path on the right down because we can't close out that little tiny loop there. This 2 over here has a corner right above it. That corner cancels out 2 of the 2's edges, forcing the corner on the opposite side, which prevents us from using these 2 edges. That will finish out this 3 here. And now this path is forced to go this way, which finishes out this 3. In general, whenever there's a corner abutting a 2, you can complete the 2. And sometimes those 2's will be in a chain. We'll see more of those in a bit. Here's another cornered 2. That allows us to finish this chain of 3's. This cell can't be filled because it would create a little island. This cell can't be filled. This one here is either using this edge or that edge, and either way the line is going to come in and then it's going to exit into this 2 cell. So one of these edges of this 2 cell must be used. We've already got the other edge, which means this edge is cleared. This edge is also cleared for the 3, so the path is forced up. Now we've got a corner going into a 2. We've got another 2 that we can complete and another 2 that we can complete. That brings these edges down, and now our 1 is finished. This one is also finished. We've got a corner going into this 2. This one will be finished like so. This 2 can only be finished this way. This 3 can be finished. This 2 can be finished. This 2 can be finished. This path is forced. Now the 1 is finished. And now we can complete this 3 chain. The 2 must be finished this way. This goes out here and then is forced down. This is forced down. This 2 can be finished. Whenever you have an intersection that has 3 X's like this in a classic puzzle, then you can put an X on the final side. In other words, I can't have a path going into here because it would have no place to go. So that's an X, which enables me to complete this 2. This 2 has a corner. This 2 can be completed. This 2 can be completed. This 1 is completed like so. And now I think the path is forced there. Okay, there's a line going into this 2 cell that must go into it. Whenever this is another pattern, common pattern. Whenever there's a line going into the corner of a 2, there must be a line escaping from the opposite corner. Why is that? Well, if a line did not escape from this opposite corner, which is here, there's only 2 possible configurations. In one of them, you've got a corner like this, and in this case, the only place this line can go is here, which would make an illegal 2. The only other possible configuration where a line does not escape is this, which is illegal as well. So whenever a line goes into a 2, a line must escape the opposite corner. And while we're at it, if you have a diagonal chain of 2s, like this, and a line is going into one of them, at the top of the diagonal chain, a line must escape at the bottom of the diagonal chain, no matter how long the chain is. So that forces a line here. Similar situation here, there's a line coming into the 2 here, and so a line must be coming out here on the opposite corner as well. This line only has one place to go. This line is forced to go down. And now we have a little island here that we can't close up, so that finishes the puzzle. I'm going to do one more easy one, and then I'll do a hard one. You can go ahead and skip to the hard one if you want to get some more advanced strategies, but I'm hoping to hit more strategies that involve 2s in particular. So in this puzzle, we've got a 1 in the corner that we can roll out some of the cells. We've got a few of those. That makes a virtual corner for this 3, which must go this way. Then we can't use this edge, and we have another virtual corner for this 3. These 2 3s form a chain like so. The 2 goes up here, and then the 2 is completed. That finishes the 1, which is completed, and we go up. I'll go ahead and fill in the zeros, which are probably the first thing you want to do because they're easy. There's a few of them, and we can make progress probably on all these zeros. So this 0 with a 3 next to it always has this common pattern. Here's another one, and here's another one. 0 with a 3, always easy to make some progress. I can see here that I can't use this edge. That forces the 1 there in the corner. And we're going up here. We've got a line going into a 3. Whenever a line goes into a 3, I'm going to do an example down here. If a line goes into a 3 and the first thing you know is it can't escape the 3. It can't bounce off the 3 because that would create a 2. And it's supposed to be a 3. In other words, it would be like this, and you can't have 3 edges. So a line that goes into a 3 always gets sucked in, and that forces the opposite corner to be filled. So it's either going to be this configuration or that configuration. Why is the opposite corner filled? Well, if the line were going into the 3 and you had an open cell here, on either one of these, you'd have something like this, which is illegal. So that opposite corner on the line going in always has to be filled. We have that situation here, so I can fill in the opposite corner on the 3, and then this one is forced to go up. This goes like that. We've got a 3 here next to a 0. This line is forced. This line is forced. That enables us to finish this 3. This 2 here already has one edge. We're going to have another edge here, and a line will be forced to escape here. So we have a line going into the corner of a 2, like I was talking about earlier, which means that, in fact, we have a line going into this 2, which means on this bottom 2, a line must escape in the opposite corner there. Similarly, a line will escape up here, but I don't know where. This 1 is complete. I'll go ahead and mark it. That enables us to complete the 3. And then we have a 2 with a corner, another 2 with a corner, and then this 2 is forced as well. These 2 2s are also forced, as is this 3. This line can only go one direction. I'm going to go ahead and do the 3 pattern here. There's only one available edge for this one. Go. This path is forced. This is forced. I have 2 diagonally adjacent ones. This is another pattern. On this one, I can't use 2 of the edges, so a line is going to be used here, and it's going to exit here, which means the far corners of this one can't be used. We're going to have a line coming in that way and a line this way. I just don't know where yet. This 2 can be completed. Okay, let's talk about cell coloring a bit. You really don't need to use it on these easy puzzles too much, but I'll go ahead and use it just to explain it. So what I'm going to do is the parts of the loop that I know to be inside the loop, I'm going to color blue. Any cell that's on the edge that has a line on the edge is an inner cell, and you can just start with those like these. And then the cells that they're connected to with no boundaries are also inner edges. We'll call the blue cells innies. When an innie is separated from another cell by an edge, then the opposite cell must be an outie. And we can color the outies. You don't have to do every single outie. You don't have to do every single innie. And so I'm just coloring the outies and innies. And so what happens is you will eventually discover situations where you didn't make a line, but it's obvious you need to make one. So here's one right there. Because I know that this cell is an innie and I know that this cell is an outie, there must be an edge there separating them. That creates a corner, which enables me to finish this 2. This line only has one place to go. This line only has one place to go. And then I can continue coloring the innie and outie cells as I make progress. The other thing that you'll notice is with coloring is that every 2 cell will have 2 yellows and 2 blue cells on as neighbors. So the vertical and horizontal neighbors of the 2, there'll always be two blues and 2 yellows. And the one that's the opposite color of the 2 is the ones, where the edges are set. And in the case of a 1, there'll be 3 of one color and 1 of the other color, and the opposite for the 3s. So this one has 3 of the same color, so those must all be cleared, and that forces an edge there. Now we have a line that is forced to go into this 3. It can't, as I discussed before, it can't turn away like that. So the line goes into the 3, and then the opposite corner of the 3 must be set, which you can also see from the 1 coloring here. And then this path is forced. We've got a corner going into a 2. Now we have an island that must be cleared. The other thing is you should know about is the outie cells that are in the interior of the puzzle must have a way to escape out. These yellow cells must escape out eventually. They can't form islands. So this is forced, and this is all forced. Here we go. I can see that the remaining yellow neighbor must be this one for this 2. So this is another way of thinking of the puzzle, is in terms of innies and outies. Very helpful. There's this very similar puzzle that uses the same tools called Cow and Cactus that you can solve pretty much completely just with coloring, which is kind of a fun way to do it. I can see here that this 2, I didn't explain what I did just now. The 2 here, it only has 1 remaining edge. Then this is forced to complete the 1. That 1 is finished. And now we come down like that. Now we've got a yellow, and that yellow must escape. So this must also be yellow, which forces an edge here. Now this 2 is complete, which forces a blue here. So that's the edge of the 1. So you can see how the coloring is another way to inform how you're solving the puzzle, another way to think about it that's useful. This yellow must escape here. And this is the opposite edge of the 2. This is going to be the 1. And this is forced. And now we've got this complicated yellow shape that must escape here. And that'll finish the puzzle. There we go. So now I'm going to do a hard puzzle. These puzzles come in various sizes, easy, medium, and hard. The hard puzzles will always require coloring to finish, or coloring strategies. That's one of the main differences. And let's get started. I'll start by doing the zeros. And now looking for, there's nothing in the corners yet. I'll look for chains of 3s that I can complete partially. Another chain of 3s down here. I can complete this too, which enables me to complete the chain of 3s. Stack of 2s. 3 with a canceled edge. 2 is finished. Corner of a 3. There's a line going into the corner of this 2, which means there must be a line escaping it on the opposite corner. And then that's going to go into this 1, which means we can cancel out the 2 opposite sides of that 1. Similar situation here going into this 2, but I can't do much with it yet. I've got 2 diagonal 3s, and you'll remember that when that happens we can do the outer edges. Now if I begin coloring at this point, I can't make a heck of a lot of progress. I can see that I've got some innies here. I've got a couple known outie cells. I have an innie cell here. And right now, everything else is up for grabs. At some point, if I make more progress, hopefully I can get my outies and innies to meet up, and that'll help us make further progress on the puzzle. I've got a 2 here that has a line going into it, so the opposite corner must have a line escaping. That creates a innie here, but I don't know the innie outie status of these ones yet. So this line is going into this 2, but I don't know if it's bouncing off. If it bounces off, then we've got this situation, which looks okay. And if it doesn't bounce off, it's either that or that. So all those look doable. Okay, here's a bit of deduction. There's a line going into the corner of this 2. I don't know if it bounces off or if it goes in. I know that if it were to go into the 2, there must be a line escaping from the opposite corner. But both the paths of egress from the opposite corner are blocked, and that means this line cannot go into the 2. So it must bounce off, which helps us complete that 3. That creates a corner here, and we complete the 2 like so. In general, when you have a 2 cell that has a corner, I call this an exposed corner, where there's no path of escape, it can only be completed in one of 2 ways, either with those 2 edges or the opposite 2 edges. And then there'll be a line coming out of that corner and a line coming out of that corner. So in this case, it's forced. This line does go into this 2, and there will be a line coming out on this opposite corner. This 1 is complete, which enables us to make a little more progress. Path is forced here. This 1 is going to use one of these 2 edges because of this line, so we can clear these 2. That enables us to complete this 3 and this line going out. And now we can make some coloring progress. There are X's here, and these are innie cells. These are all innie cells. These are outie cells. And now we have a forced boundary. This path is forced. That edge is forced. This path is forced up. So that's an innie. When a cell is on the edge, you can treat the outer cells as outies. In other words, this imaginary cell below this 3 is an outie and would be colored yellow if I could color it in. So I can see that this 3 has 2 outies on either side, which form a virtual corner. So we can go ahead and fill that corner in. I still don't know which way this path goes, so I don't know the status of this area yet in terms of its innie outiness. One thing I like to do on these puzzles when I'm feeling a little stuck, as I am at the moment, is go around and identify X's that I've missed. Sometimes that'll help, and having just filled in this X over here, well, there's also some more here. So basically I'm just finding corners and putting X's by the edges that can't be used. Having done that over here, I see that this 1 has a only one point of egress, which is the upper left corner. So it's going to use either this edge and go out that way or that edge and go out that way. So that forces the path to go like this. And now we can do the opposite corners of this 3 because we have an incoming edge on the 3. Now we have a line going into a 2, so there must be a line coming out of the 2 at the opposite corner. That finishes this 2. Then we can finish this 2, finish the 3, finish the 1. And we've made some pretty good progress here. Now we've got a little island we need to prevent. We've got a line going into this 2, so there must be a line coming out of the opposite corner, but this one's blocked. Now we can complete this chain of 3s. We can do the opposite corner on this 3. And now we can do some coloring. Whoop, not that much. So coloring and X's are a good thing to do when you're feeling a little stuck. And now I can already see that we've made a good bit of progress on this puzzle, and now we can color in quite a bit more of it. This entire area is outie, innie. This 2 has blue, blue, yellow, so this must be yellow, which of course from the edge we already know that. This 1 is forced. Whoop, that's outie, or innie. Wait a minute, I made a mistake. Oh, this edge is not forced. This goes like that. Oh, there's definitely something wonky here. I have made a mistake. I'm gonna check to see how bad my mistakes are. Oh, it's just this one edge here. So I did. So what I did was just now is I did check answer, which tells you that there's a mistake, and then I did reveal answers, which shows you the mistake. You can also in the settings down here have it auto check the answers. I've been leaving it turned off. I normally have that turned on. I have it turned off right now just so that I can show you examples without a bunch of red lines. So that is not a line, which means this is actually an outie cell, and this goes like that, and that makes a lot more sense. Any 3, such as this 3 that has a corner set, must have a line escaping in the opposite corner in these classic puzzles. And since that line can only escape one way, we know what it is, and that forces this cell to be an innie, as well as this cell. Now we've got a 3 with a corner. This can only be filled in 2 ways, or an exposed corner. So it's either going to be that, or it's going to be that. And either way, this edge is forced to exit at that point, regardless of the one we use. That forces this path here, and now we have an innie that must escape. Sorry, an outie that must escape. I apologize for transliterating my innies and outies. So this is all forced like so. When you have a known innie cell on the edge, you can always do the outer border like that. This 2 is already complete, so that finishes that corner. This is forced. This 2 can be completed, which forces an outie. Now we've got another corner here. Now this corner forces the configuration to either be that way or this way. And this way is illegal because it doesn't work with this 3. See that? I can't finish the 3. when there's a corner. So it must be this way. That finishes this 3. So this is an outie. This is an innie. That's an innie. That's an innie. That forces this corner, forces this path of egress. This is a forced innie because of the edge there. We can finish this too. And we can finish this path here. Now, we've got a situation here where we've got a blue island, and blue islands like this, any areas must be connectable to all the other innies in some fashion. So this would be illegal because it would isolate this landmass here. So it's got to be connected through this bottleneck, and so bottleneck prevention is definitely one of the things that you want to be looking for. Okay. Similar situation here. We've got a bottleneck that we want to prevent, so that forces the innie area to go out here, and it must even go out all the way to here. That forces this edge on this one, which means this is also going to be outie. We're going to use this edge on the 2, which means we can't use that edge, and we've got a completed area up there. This path here is known. And now this blue area has to connect to the rest of the puzzle in some fashion, either up through here or this way, but I'm not sure which way yet. I can see that this is out. And I can see that this path is forced because of this corner and that corner. So there's only one way to go here. That tells us that this is an outie. Now we've got a forced paths, and we can complete the puzzle. So that's a hard puzzle. As you can see, we're making use of more advanced logic on the hard puzzles, and coloring is definitely a crucial part of filling those. If you can do it without coloring, but it's definitely significantly harder. So these are the classic Slitherlinks. I will be doing another video on the variety Slitherlinks, such as the ones in the second half of my Kaleidoscope puzzle book, also available on the website. They make use of very similar rules, but the rules are generalized more, and I'll talk about that in the other video. Happy puzzling!